Okay, so in this lecture, we're going to continue with our discussions on topics in acoustics. So we're going to talk about resonance, sound velocity, wavelength, talk a little bit about phase and how phase interference affects sound. And then we'll move on to complex sounds that can be periodic and aperiodic, and briefly touch on the source filter theory. Resonance is an important concept within acoustics. Um, and in physics, it refers to the tendency of an object to oscillate with a larger amplitude at certain frequencies than others. And the frequencies with which it prefers to vibrate or oscillate with a higher amplitude is what we call as a resonant frequency. The resonant frequency for any object depends on its mass and well, stiffness properties. So it depends upon the physical properties of the object itself. And why we see a larger amplitude at this resonance frequency is it's at that frequency where the amount of damping is minimal. Okay, and examples of well, dramatic examples of resonances are all around us. You probably might remember, or we might have heard of opera, especially tenor singers who can shatter a wine glass from a distance just with their singing. And there's a short video in this hyperlink where you can look at that over here. Other examples of resonances are all around us. You probably might um, hear again the bass of a car stereo. And you might even, when if you're the person playing that music, you might feel the vibrations on your steering wheel um, or in your chest, depending upon how low frequency you're looking at. Other examples of resonance could be like when you pictures or ornaments falling down from your shelf when you play, or somebody in your home plays loud music. You might also remember of incidents where there's windows of your glasses the glass on, pardon me, of your windows shattering, especially when there's some vehicles passing by on a nearby highway. And of course, you can remember blowing tones on the top of a beer bottle. And one thing you might notice is that as you drink the beer bottle, the tone that you make with the beer bottle changes. Um, so it might start with a high note, and as you drain the beer, or could be well, any other fluid, um, the note gets deeper and deeper, gets lower. So those are some examples of resonances. Resonances are also play in your ability to well, push a child on a swing, push a car out of a ditch. Historically, one dramatic example of resonance that's often quoted is that Tacoma's Narrows Bridge, um, which collapsed actually because of air, um, uh, wind-induced vibration. You might you can see a short video about. Okay, related to um, of course resonance is the concept of sound velocity. Velocity pretty much refers to the distance traveled within a set time. So it's the unit for velocity would be meters per second. The velocity of any wave depends primarily on the medium. It depends upon the properties of the medium, namely density and the temperature of the medium. Um, the velocity of sound traveling through air, the common medium in which it travels, is around 343 meters per second. Sound waves travel faster through um, solids and liquids than it does through gases. For example, the velocity of sound is as high as 1,480 meters, almost fourfold that of sound traveling in air. And a good analogy of explaining how and why sound travels faster through mediums like solids than more rarefied mediums like air would be looking at this Newton's cradle. All of you guys would have seen this play apparatus where with the balls, when if it's stimulated on one side, it results in pushing the ball on the other side. So almost the end ball moves instantaneously when there's no gaps between those balls. And that would be like how the particles are in within a solid medium. But imagine that you're leaving one ball in between the series. So there's more gap between the balls. So that would be an analogy of the particles or the molecules within air, for instance. Now, if you were to stimulate this Newton's cradle with lesser balls and it's more space between the balls, it's going to take a longer time for each ball to stimulate the next ball. So the time with which this disturbance that you started in the first ball, it's going to take a while before that disturbance reaches the last ball. Such is the case with sound traveling through a dense medium versus a more rarefied medium. Sound travels faster through when the particles are closer to each other, so and each disturbance travels instantaneously to each other, while sound travels slower in mediums where the particles are separated by a distance. The velocity of sound is often confused with frequency. Okay. Often you would hear people quote that high frequency sounds, let's just like 8,000 hertz, travels faster than a low frequency sound, say like 100 hertz. That is not true. Uh, Velocity and frequency are distinctly different quantities. While velocity refers to the distance traveled per second, frequency refers to how many cycles occur per second. So you can actually have a low frequency sound like 10 hertz um, that travels through a solid medium faster than a high frequency sound like 8,000 hertz, which traveling um, through a medium like air. So it's the medium that determines the velocity of a sound. And given the same medium, and this is an important point, given the same medium, um, any given frequency would travel with the same velocity. Okay. So if the medium is uniform, such as if it was air, all the frequencies, 20 hertz, 200 hertz, 2000 or 20,000 hertz, would travel with the same velocity. Okay. And that's the reason why we enjoy music. Imagine that some sounds, if you're in the same room playing a stereo, imagine the higher frequency sounds reaching you faster than lower frequency sounds. Now, of course, you're not going to appreciate that kind of music. How further do the sounds reach? Well, that's a different concept. Um, Lower frequency sounds have the tendency to travel further than higher frequency sounds. They travel, both low frequencies and high frequency sounds travel with the same velocity, but lower frequency sounds, by virtue of their longer wavelength, something that we're going to talk about in a bit, they can move around objects and travel further than higher frequency sounds. Okay. Our knowledge on sound velocity has actually been used in a lot of technology around us. Um, on an evolutionary basis, members of the animal kingdom have actually used sound velocity for echolocation purposes. For instance, like the bat using ultra high frequency sounds to bounce off moving uh, objects like an insect to calculate the distance or the speed with which it's traveling um, uh, for food. Um, Other animals have also used echolocation, such as like killer whales and elephants and orcas. It was only recently in this century that actually we've used this sound waves um, you know, to navigate, for instance, mainly in the sea. You probably would have heard the sonar devices that are used in ships and boats. The sonar stands for actually sound navigation through audio um, responses. Here, the device actually throws out a low frequency sound um, that that's bounced off the floor of uh, or the bed of the lake or the ocean. And depending upon the time it takes for it to reach back the device, um, uh, it, it gives an idea of how further away the floor of the ocean or the lake is. A similar concept was actually used by older automatic focus cameras. Um, so what the camera does is actually throws out an ultra frequency sound, in this case a high frequency sound, bounces off objects, and depending upon the time it takes, it determines how further that object is and automatically adjusts or zooms in or zooms out. Um, and nowadays the cameras actually use not an ultra frequency sound, but it uses infrared um, because it's lesser diffracted by other objects in the environment, and so it gets a better focus. Um, for here's an example that you guys can work out to practice uh, velocity of sound. Let's say if a sound wave returns to a camera after zero point 0.2 seconds after leaving the camera, um, calculate how far away that object is. Okay, we know that the velocity of sound is 340 meters per second. So in other words, in 1 second, sound travels 340 meters. Um, so pretty much you have to calculate how further does it travel in zero point 0.2 seconds. Okay, well, zero point 0.2 seconds refers to the distance that it travels uh, two ways. So it goes to the person, let's say our object, and then it bounces back. Um, so so the answer would be 340 times zero point 0.2, 68 meters. That would be the two-way. And the right answer would be 34 meters, and that would be the distance between the object and the camera. Another important concept in sound is the wavelength. Now, wavelength refers to the distance between the two same points on a wave, and the unit for wavelength is meters. Okay, so the wavelength could be, for instance, uh, points between um, zero phase over here and over here, so that could be the wavelength. Or it could be the distance between when the wave is 180 degrees, 180 degrees. That could be the wavelength. So from 0 degrees to 0 degrees, or from 180 degrees phase to 180 degrees over here, the distance it travels through pretty much one cycle of the wave would be a wavelength. So similar to period, wavelength has a reciprocal relationship with to frequency. So higher the frequency, shorter the wavelength. So higher frequency sounds have smaller wavelength, while lower frequency sounds have longer wavelength. And there's a fixed relationship between wavelength, velocity, and frequency. Okay, such that frequency is velocity over wavelength. Now, velocity is constant for any given medium. So if we are considering air, that velocity of sound is about 340 meters per second. And so that's constant. Um, so if you keep that constant, if you change frequency, if the frequency increases, the wavelength, which has a reciprocal relationship, has to go down, and vice versa. So if frequency decreases, the wavelength will increase because velocity is constant in this relationship. Okay, so the wavelength of 1,000 hertz pure tone is, if you were to fit that into this equation over here, would be 0.34 meters, while that of a 2,000 hertz pure tone would be half of that. So pretty much when the frequency doubles, the wavelength becomes half. Wavelength in equations is expressed by the lambda sign. So as you move from low frequencies to high frequencies, the wavelength actually decreases. So you're moving from a longer wavelength to a shorter wavelength for high frequency sounds. So, and this relates to how further do sounds travel. So now low frequency sounds have a longer wavelength. Um, so they can move around objects that are in between. And that's the reason why you hear that lower frequency thump thump thumping sound at a longer distance, and then the higher frequency notes. Uh, and the reason why elephants and whales and orcas seem to be using these low frequency sounds for communication, because their intent is to reach their herds, which are miles and miles away. Okay. The higher frequency sounds, they get easily diffracted uh, by smaller objects because their wavelength is short. So they get bounced off by even small objects, and they have the lesser chances of reaching longer distances. Okay, and bats have evolved to use that because they want their sounds to be reflected back by those flying insects, so they can locate them. Um, so musical instruments that produce low frequency sounds have to be longer because they result in longer wavelengths, while musical instruments that produce shorter wavelengths result in a higher note. So there are some gongs apparently in monasteries, Buddhist monasteries in Indonesia. That are almost 30-35 meters diameters, um, and they produce this very low frequency 10 to 12 hertz sound. It's almost like a murmur that's you feel as a vibration. You don't hear that as a sound. On the other hand, smaller the musical instrument, like a short whistle, it's going to result in a higher note. Another important concept in acoustics is phase. Okay, now phase refers to the relationship um, between waves. Okay, um, the instantaneous location of a vibrating object is what we call as phase. Um, And when you're talking about two or more waves, you're talking about waves that can be in phase or out of phase. Uh, so here you're seeing an illustration of pictures of a skipping rope that are making what we call a standing waves. Okay, and standing wave is an important concept that's related to phase. Um, we in our previous lecture we talked about a sine wave being the simplest form of a tone. Another kind of wave that's quite similar to the sine wave is a cosine wave. Okay. Now the difference between a sine wave and a cosine wave is a cosine wave is 90 degrees out of phase to that of a sine wave. Okay. Independently, if you were to listen to, let's say, an 100 hertz sine wave, it would not sound any different than a 100 hertz cosine wave. However, if you were to play them together, that's when these waves, since they're out of phase, they're gonna that that sound is it's gonna sound the complex sound that's creating is gonna sound different. Okay, so that brings us to standing waves. So standing waves are produced when two traveling waves, two sinusoidal waves, interfere with each other when they're traveling in opposite directions. Okay, so when that happens, they create an interesting phenomenon that kind of gives an illusion of the wave not moving anywhere, just standing at the same point. So in this animation over here, you can see a blue wave, and if you were to just concentrate on the blue wave, you can see that the blue wave is moving from, well, left to right. At the same time, we're introducing another wave, a green wave, that's moving from, well, right to left. Um, over here in the opposite direction. So if you were to make these waves at the same time, and you can note that they're of the same frequency because they have similar wavelengths and similar periods. If they're produced at the same time, it's going to result in a standing wave that's denoted by this black wave over here. And if you were to tease out the standing wave, it actually looks like this. So there's going to be some points within the medium where there's no movement of those particles at all. So namely, it's going to be these points over here, this point, and then this point over here, and that point over here. So where the particles are not being displaced at all, and we're going to call them as nodes. And between the nodes are going to be particles that are going to be displaced from a positive maximum to a positive minimum. Well, positive maximum and a negative maximum. Pardon me. So it's going to be a positive maximum over here and a negative maximum over here. So these are what we call as standing waves, and that those are because they're the result of constructive and destructive interference, uh, and of those two waves. Okay, here's another illustration showing the nodes when there's two traveling waves moving in opposite directions. If they were to play together, then you're going to have these nodes, points where there's no displacement at all. And between those nodes are going to be those antinodes where there's a change between a high positive and a high negative. Now, the concept of standing waves is used in some good headphones, what we call as noise cancelling headphones. Pretty much what a noise cancelling headphone does is it captures a sound um, and it reverses the phase of the sound and plays it back. Okay. So in that way, it's canceling out the sound through this concept of destructive interference. Okay, and you notice that those noise canceling headphones are pretty effective only for lower frequency sound, so they work pretty good when you're traveling on a plane. And you'll see that the low frequency background noise seems to be reduced quite a bit. Um, so it does use the concept of phase and of standing waves. I've got a cool video over here. Well, as it says, it's cool. Where actually you're seeing, visually seeing the concept of constructive and destructive interference playing out on sand particles that are spread at the top of a membrane. So far we've been talking about simple waves or sine waves or pure tones. And if we have just one more than one, we talked a little bit about interference and phase relationships. Most of the sounds that are around us are actually complex in nature, so they have energy at a number of different frequencies, and they are of different amplitude and different phase relationships. A mathematical way of decomposing a complex sound is what we call as Fourier analysis. Um, So when you capture a sound, and if you have a software that does this analysis and throws out the complex sound as a spectrum, actually it does this Fourier analysis to tease out all the frequencies out of this complex sound. Now there's two types of complex sounds. You've got a periodic complex sound and an aperiodic complex sound. Now periodic complex sounds such as our voice, um, are vowels in speech, and music. Um, these are complex sounds that have they repeat regularly over time. Uh, they have this periodicity um, in terms of the sounds repeating. Other sounds are what we call as aperiodic. They also have a number of frequencies, but they vary randomly over time, and typically we group them as noise. So sound of a waterfall, or the background noise um, in traffic, some of the consonants like our fricatives and your affricates. If you were to hear them in isolation, they actually might sound like noise. So here we're looking at waveforms over here. So we know that's a waveform because we've got the time axis over here and the x-axis, and the amplitude as a y. Adjacent to that is a spectrum of the same sounds. Here we've got frequency in the x-axis and amplitude again as your y-axis. So in periodic complex sounds, you can see that events repeat itself pretty regularly. And if we were to look at the spectrum, there you can see that distinct frequencies can be separated out. Now, aperiodic sounds, there is no set pattern in which the sound repeats itself. So this could be something what we call as a white noise, or a wideband noise. And if you were to look at the spectrum, you'd see that it pretty much has energy across all the frequencies, and there's no emphasis in any of the frequencies over here. Periodic sounds have a tonal quality to it, and while aperiodic sounds don't have, you can't assign a tone to it. Um, Periodic sounds like say our voice, our vowels, um, you can hear uh, a male ah vowel and versus a female making an ah vowel or a child making a ah vowel. Um, you can assign a tonal quality to it. So, namely, the male voice having a higher frequency, uh, a lower pitch, while frequencies, the children and females have a higher pitch or higher tonal quality. But if a male, an adult male, an adult female, and a child were to produce a sound like s, you would notice that you wouldn't be able to assign a tonal quality um, to those fricatives or affricates. So when you have a complex sound that's composed with tones, um, and 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 they are periodic, then the lowest frequency, which typically has the highest amplitude, is what we call as a fundamental frequency. Okay, so periodic sounds have a fundamental frequency. aperiodic sounds don't. Within a periodic complex sound, if you were to look at the spectrum of that, um, as I said, the lowest frequency, which typically has the highest amplitude, would be a fundamental frequency. But there's going to be energy in integer multiples of this fundamental frequency. Um, let's say the average human adult voice has a fundamental frequency of 100 hertz. Um, you're going to see energy in the spectrum at integer multiples of it, namely 200, 300, 400, and so on. And these are what we call as harmonics. Okay. Now, if you were to pass a periodic complex sound like the human voice um, through any given medium, now there's going to be certain frequencies based on the resonance of that medium that are going to be emphasized, while some harmonics are going to be suppressed. So the output, by the time this complex sound reaches like a human, let's say, auditory system, it's going to sound different than how it is in the source. So that brings us to the concept of the source filter model of speech production. Okay, so if you were to tease out the complex sound right at the level of your vocal folds, let's say an adult male um, larynx, and if you were to look at the spectrum, it might look like this. It's going to be a periodic complex sound. It's going to have a fundamental frequency close to the lowest frequency in which the vocal folds are vibrating. But it's going to have energy at integer multiples of that fundamental frequency, and there's going to be a systematic decrease in its amplitude, like over here. But the sound that's produced by the vocal folds has to travel through your vocal tract, and that's what we call as a filter. Okay. Now the filter, depending upon the length and the size of the vocal tract, it's going to prefer to uh, emphasize some frequencies and de-emphasize or suppress some frequencies. So that by the time this voice travels through the vocal tract, the output is going to be shaped differently than how it was at the level of the larynx. Okay, so you can see that the relationship remains the same. In other words, you do have energy at 100 hertz, 200 hertz, 300 hertz, 400 hertz, so on. By yeah, you can see from those lines over here. But there's some amount of shaping that's done to the overall spectrum uh, because of the resonance characteristics of your vocal tract. So these peaks is what we call as formants. Okay, so you have a fundamental frequency, um, and you also have formants. Okay, and these formants are characteristic of the filter or of your vocal tract. And according to the source filter theory, uh, the source characteristics are quite independent than the filter characteristics. Okay, so for example, this is a spectrum of the vowel ah that's made by an adult male. You can see that the fundamental frequency is 100 hertz, and then you can see energy 200, 300, and so on over here. Now, women and children have a higher fundamental frequency. Um, so women typically have a fundamental frequency as 200, while children can have, very young children can have fundamental frequencies as high as 300 or 400 hertz. So that means that their fundamental frequency of women is it's higher, than say 200 hertz over here, or 250 hertz over here, and the second harmonic is going to be 400 hertz, um, and the third harmonic 600 hertz, and so on. So they're going to be spaced wider than those of men, and hence that's why some consider the men voice, the voice of men more kind of rich because the frequencies are more concentrated or they're more closely spaced than that of women or children. But if both the male speaker and the woman speaker were to produce the same vowel, let's say they're making the vowel E over here, um, the resonant peaks are the shapes, the shaping by the vocal tract is going to be similar. So even though the frequencies are different, the frequency composition of the source are different, by the time it goes through the vocal tract, the overall shaping is going to be similar. And that's why you can identify it as the same vowel, R or E, be it produced by a male or a female. So even if the fundamental frequencies and harmonics are different, the shaping um, that's done by the vocal tract is similar, resulting in the same percept. And that's what we call as a source filter theory. The source refers to the fundamental frequency and the output from your larynx, which is shaped by the filter to result in the different speech sounds. Because the resonance of the vocal tract can also be altered by changing kind of the medium. Um, so when we are talking regularly, the medium within our vocal tract is filled with air. And let's say that uh, in air, sound travels at the velocity of 340 meters per second. But if you were to replace that medium with a different medium, such as like say helium, which is much lighter um, than air, uh, the velocity with which the sound travels is going to be changed. It's going to be much faster. Um, so while in air sound travels at the velocity of 340 meters per second, it can travel close to about 900 meters per second um, um, when it travels through helium. So that's the reason why your voice changes when you're talking through helium. It's not that the rate in which your vocal folds vibrate uh, changes. In other words, your fundamental frequency is going to stay the same, be it your vocal tract filled with air or with helium, but when it travels through the vocal tract, there's going to be a change in the emphasis in the frequencies that it prefers to vibrate in. So this could be the voice in air, but if that air is replaced by a helium from like say a helium balloon, the timbre or the tonal quality is going to change, making it sound like a mini voice. And again, this is an example of how resonance comes to play. Now, instead of changing the length of the vocal tract, you're changing the velocity of the sounds traveling through the vocal tract, resulting in a higher note.